Historically, Argonne is kind of famous for materials. I think it's material synthesis, kind of materials development, optimization of materials, things like batteries and such. I'm an assistant scientist here, and I actually work entirely within QNext, which is our quantum center that's based out of Argonne. And so a lot of the work that we do in-house is trying to grow materials on site. I then, with my team, will fabricate them into various devices to do measurement, to send photons into fibers that are on site or going off site to our kind of neighboring institutions like University of Chicago, Fermilab, et cetera. And then we kind of have a full closed cycle loop in order to be able to develop. I think that's the goal, the dream for every research team or collaboration.
There are a lot of interesting research happening at Argonne, cutting across different focus, next generation quantum materials and devices, as well as sensors, and then quantum communication development, as well as on the computation side and simulation for quantum computing. So a little bit that I primarily focus on is on the quantum material and networking, and it covers both fundamental physics as well as those applied side. It kind of goes side by side. So Argonne is aimed to enable these large-scale quantum communication networks.
The recently established Argonne Quantum Institute actually coordinates research activities in these areas, and it also helps with enhancing our partnership with industry, academia, and other national labs. We are actually establishing a 5-node campus-scale Argonne Quantum Network with connectivity to multiple other institutions in the Chicagoland. We have connectivity to Fermilab, have connectivity to University of Chicago. We also have connectivity to Starlight, which is an internet exchange point in downtown Chicago. So with all these connectivities, the Argonne Quantum Network is becoming a hub in the Chicago metro area. So one can use this Argonne Quantum Network with all its connections to actually test quantum networking devices and protocols in a real-world setting.
We're collaborating with a number of university partners from all around the United States, a lot of industrial partners, and there is a kind of exchange of information that is really exciting. We're able to have kind of cutting edge conversations on, hey, we collected this data, we don't really understand it, or, oh, we have some preliminary work that we've done that it would really help you. Here, why don't you talk to my graduate student or postdoc that is, been working on this for 2 years, and you really wouldn't know about it because it hasn't been published yet. That way of advancing things is fantastic, and the rapid exchange of information there is critical for pushing everything forward.
What's unique to Argonne is we're doing both the fundamental material science with the defect discovery, leveraging tools like the synchrotron and the facilities like the Center for Nanoscale Materials and the Argonne Leadership Computing Facility, and really bring that all under one campus to sort of really tackle the challenge of scaling these semiconductor qubit systems into real technology.
Argonne has amazing facilities, including the Center for Nanoscale Materials, but I especially use the ALCF and their computational resources. Argonne has access to some of the largest supercomputers in the world, and we use these to simulate quantum systems and, in fact, interplay quantum systems with classical resources to really stretch the limits of what's capable.
The other thing I want to also highlight is the Argonne Quantum Foundry, and that is funded by the Department of Energy Office of Science, part of this QNext Center, coming through this National Science Initiative.
The Argonne Quantum Foundry has additional capabilities to do very specific things for quantum materials. And then, of course, advanced leadership computing has simulation capabilities that are basically unparalleled, kind of anywhere in the US that isn't another DOE facility.
Another distinctive aspect of the quantum networking research at Argonne is our approach is truly multidisciplinary. And with computer scientists, experimental and theoretical physicists, mathematicians, network engineers, all of these people actually work together to design a scalable quantum network.
The future will be really exciting. Quantum information science is multidisciplinary. You need people of tons of vast different backgrounds to be able to work together. There are a lot of unanswered questions, so you need that level of engineering in place, and also how you link different computers together to get it to a large-scale computer, for example. And then the development of quantum network that has already happening at Argonne will play a role because it allows you to interconnect different computing systems.
I know that this ecosystem development, everyone want to create the next Silicon Valley or what have you, is happening all over the country, but I think this is the best place to be for quantum research right now. And you can see it on the number of entities that are always reaching out saying, we would love to learn about what you're doing. We'd love to see how we can work with you, because they see that the critical mass, I think, is being achieved. And this is really making this a real hotbed in that kind of greater Chicago area. Everyone wants to be here, or if companies aren't here, they're trying to figure out how they're going to be here.